Okay, so this is set B, I think. Yes, this is set B from chapter 16, number 4. So let's do number 4 here. We have 100 draws will be made at random with replacement from one of the following boxes. Your job is to guess what the sum will be, and you win $1 if you are right to within 10. In each case, what would the guess be? Which box is best? So your guess is going to be the expected value of the sum. And we're drawing out 100 times. So with this, you need to find the expected value sum for this box, and this box. So let's do that just with the first one. The expected value sum is equal to the number of draws times the average of the box. So let's find the average of the box. 1 plus 9 divided by 2 is 5. And that's actually the average for all 3 of these boxes. 4 plus 6 divided by 2 is 5. 5 plus 5 divided by 2 is 5. So we're going to do the number of draws times the average of the box. 100 draws times 5 is 500. And we're going to guess 500. Since the number of draws and the average of the box is the same on all 3 of these, we're going to guess 500 on all of them. And so that's what you got, 500. Which one's best is going to be option 3, because you're guaranteed to get 500. You're going to be drawing out of that box, and every time you draw out of that box, you get 5. And since you're looking at 100 draws and each of those draws is going to be 5, you're guaranteed to get 500. So option 3 is the best one for that. Let's see, next question. Let's do C, number 1. Okay, C number 1. So consider the following 3 situations. A box contains one ticket marked 0 and 9 tickets marked 1. A ticket is drawn at random. If a 1 shows, you win a panda bear. A box contains 10 tickets. Well, I drew that one too big for sure. Okay, this one. The box contains 10 tickets that are 0, 90 tickets that are 1. If it shows a 1, you get a panda. So on this one, there's 90% of the tickets show a 1. On this one, same thing. 90% of the tickets show a 1. And then this last one, a box contains 1 ticket marked 0. And 9 are marked 1. The 10 draws are made at random with replacement. If the sum of the draws is equal to 10, you win a panda. So let's find the sum of the draws by doing the expected value. So the expected value is going to be equal to the average times the number of draws. So we've got 10 draws times an average of, let's see, we've got 0 plus 1 plus 1 plus 1 plus 1 plus 1 divided by 10 is going to be 0.9. You can do 1 bar stats with a frequency list to get that if you need to. And then that makes 9. Our expected value. Well, we're looking for the sum equals 10. So let's find the shade norm, the area or the chance that it equals 10. So let's do z-score. 10 minus 9 divided by standard deviation or standard error, which I didn't calculate. So let's do that. Standard error is going to be equal to the square root of the number of draws times the SE. So I'm going to have to type that into one of our stats. Oop. Okay, so okay, I forgot to type in the frequency list. So we've got 1 and 0 and 1091 ones. Nine ones, 1 0. Keep hitting the wrong buttons. Okay, here we go. Frequency list is list 2. Calculate the standard deviation is 0.3. Square root of 10 times 0.3 is 0.95. Minus 9 divided by 0.95 gives us 1.05. So we're going to do shade norm. I am out of space here. We'll write it here. It has to equal 10. Oh, so we're not looking for above 10, huh? Which means all of this was actually just a waste of time. Okay, so we expect it to equal 9, not 10. So this is not what is expected, which means we can compare now knowing what we expect. I guess you can calculate the chance that it is equal to 10. Sorry, I'm just going to read the back of the book here, because this one does have me a little stuck as well. So we are on chapter 16. Set C, number 1. Options 1 and 2 are the same. Yes, we got that. 90%. 90%. 3 means that all 10 draws must be 1. Okay, yeah, so in order to get a 10, you have to draw 10 tickets and they all have to be this. So you've got a 9/10 chance of it being a 10, of it being a 1. This has to happen every single time, 10 times. And that is going to be less than 90% chance if you calculate it. So that's why 3 is worse than 1. So these are the same. This is better. Sorry, that one did get me stuck for a minute, but you can see I use the back of the book to figure it out. And that's frequently with this homework, that is what I do, is I check the back of the book, read their explanation, and then work backwards to get to that same conclusion on my own. Okay, let's do some review questions here. Actually, no, let's do number 3 from set C. Okay, in one version of Chuck-a-Luck, that's a fun one to say, 3 dice are rolled out of a cage. You can bet that all 3 show a 6. The house pays 36 to 1, and the bettor has 1 chance and 216 to win. So this already told us our probability of getting all 3 sixes, a 1 out of 26, or 1 out of 216. If it does happen, it pays 36 to 1. So this says, suppose you bet 10 times, sticking $1 each time. So if you win, you get $36. If you don't, you lose that $1. Your net gain is like the sum of 10 draws made at random with a replacement from the box. What are we supposed to fill in that blank? Oh, we're supposed to fill out the box. Okay, so you have $36. And only one way to win that $36. And then the other 216, so the others out of that 216 options. So 215 options, you lose $1. So this is your box. And yeah, that is a terrible game. This should have been negative $1, not positive $1, sorry. Okay. Let's do some review questions. So let's do review number 1. A box contains 10,000 tickets, 4,000 zeros, and 6,000 ones. 4,000 zeros, 6,000 ones. And 10,000 draws will be made at random with replacement from this box. Which of the following best describes the situation and why? Okay, we're making 10,000 draws with replacement. And since it's with replacement, there's no guarantee that it's going to be exactly 6,000. If it was without replacement, you would be drawing every single ticket out of there. But it's not without replacement. So it's possible you would draw 4,000 10,000 times. I mean, that's 0% chance of happening, but that is a possibility. So that's false. The number of ones is likely to be equal to 6,000, but there is also a small chance it will not be equal to 6,000. The number of ones is likely to be different from 6,000, but the difference is likely to be small compared. Okay, it is option 3. This refers to the law of averages. You're probably not going to get exactly what you expect, but you're going to get close to what you would expect because it's such a large number of draws. So that's just law of averages. A gambler, so now we're going to do number 3. A gambler loses 10 times running at roulette. He decides to continue playing because he is due for a win by the law of averages. Okay, that is false. That's the gambler's fallacy. There's no memory of what happened in the past. So he's not more likely to win on the 11th round just because he's lost 10 times in a row. So they're both wrong. The gambler is wrong because of the gambler's fallacy. The table has no memory of what it's done in the past. The bystander is wrong because luck has nothing to do with winning or losing at gambling. It's all statistics. And let's do number 4. Okay, a die is rolled some number of times, and you win $1 if it shows an ace or a 1, more than 20% of the time. Which is better, 60 rolls or 600 rolls? Okay, the chance of getting a 1 is 1 out of 6, or 16.7%. So we want more than 20%, which means more than what you would expect to get. The chance of getting more than what you would expect is going to be with a smaller number of rolls. With a higher number of rolls, you're going to get closer and closer to that expected value. So you want to do the 60 rolls there. As an A, but this time you win $1 if the percentage is more than 15%. This one would be 600 rolls because 15% is just below 16.7% and we're more than. So you're going to get closer and closer to that 16.7%, which satisfies the criteria that it's more than 15%. Okay, same thing here. You win $1 if it's between 15 and 20%. So we're going to get closer and closer to that 16.7% if it's more than one roll. Let's see, this one, you win $1 if the percentage is exactly 16.23%. Okay, when it says exactly, that means you want to do a smaller number of rolls. So with a larger number of rolls, the chance of getting exactly what you want is pretty slim. You're just going to get close to what you expect. And let's do number 7. A quiz has 25 multiple choice questions. Each question has 5 possible answers, one of which is correct. So we have 5 possible answers here, and only one of them is correct. A correct answer is worth 4 points, but a point is taken off for each incorrect answer. So if you're randomly guessing, you have a 1/5 chance of getting 4 points and a 4/5 chance of losing 1 point. So we can draw a box for that. 1 chance of getting 4 points, 4 chances of losing a point. So a student answers all the questions by randomly guessing. The score will be like the sum of 25 multiple choice questions. So we're drawing out of the box 25 times from this box.